Hi, welcome to Recitation Week 11. Today I will be discussing the root locus method. So in summary, root locus is a method that can be used to design a controller gain for a closed loop nonlinear system. So for us to use this root locus method, so we need to define what kind of system that we are considering. Here we assume that the system is given as follow. So we have a controller gain k which we want to design, and we have a plant or transfer function of the system. Also we have some feedback transfer function, say h of s. As usual, we have input u of s and output y of s, and we have negative feedback, so this is minus and this is plus. Okay, so this is our setup. We have a controller gain k which we want to design. G of s is the given transfer function of the plane, and h of s is the given transfer function for the negative feedback system. And the purpose of root locus is to plot the location of the poles of the closed loop system as k varies from 0 to infinity. Okay, so starting from 0 for k, so k equals 0, what are the poles of the closed loop transfer function as k is growing from 0 to infinity. So today I will be discussing some of the rules and some of the steps that can be used to construct the root locus of this system. So usually g of s is given, h of s is given, and our task is to draw the root locus. Okay, I hope you guys already read or studied the materials from Dr. Chow. So he already posted I think 3 lecture notes on root locus so far, and today I will be reviewing some of these rules from his lecture notes, but I tried to summarize it, so it should be more brief, and I will also show how to use that in an example. Okay, so first of all, we need to define some terminology or some variables. So the first terminology is OLTF. So it stands for open loop transfer function. Okay, so for this kind of system, what is the OLTF? So OLTF of the system is simply g of s times h of s. Okay, so it's defined as g of s times h of s. The second variable is n p or n sub p. N represents the number of poles of the open loop transfer function. So it's the number of poles of the LTF. Similarly, we have number of zeros, n sub z or nz is the number of zeros of the open loop transfer function. Another term is CP or characteristic polynomial is defined as 1 plus k g of s h of s. So these are standard terminology in root locus. So we might use them, we might not. It depends on the types of the problem, like what is g of s, what is h of s, so how many poles are there, how many zeros. Okay, so I hope you already familiar with this terminology. Now I also have some rules. So this is terminology and definitions. Next, I also have some rule. So this is different than the rules given by Dr. Chow in his lecture notes. This is just a simple rules when we need to construct root locus rules. We have some rules, so I will put underline there, underline. Okay, so the first rule is that root locus, okay, so I will move it here and I will define another. So RL stands for root locus. Okay, so root locus or RL is always symmetric with respect to the real axis. So remember that in Laplace domain we have a real and imaginary axis. So real is the horizontal line and imaginary axis is the vertical line. That's the first rule. So if your root locus is not symmetric with respect to the real axis, then you make a mistake there. Okay. Root locus. The second rule is that the root locus has n number of branches. Okay, where n is equal to the number of poles of the open loop transfer function. Okay. Third rule is a simple one. So any pole of the OLTF is marked with cross or X and zeros with circle or O. Okay, so don't forget that, because this is a very important convention. That any pole is indicated by cross or X and any zeros are indicated with O or small circle. Okay, the next rule is that it's branch. So what is branch? I will demonstrate it later, but the fourth rule says that each branch starts at OLTF poles and ends or terminates at OLTF zeros, or if there is no zero, or infinity. Okay, so these are the four rules. So be familiar with these rules. Next, I will discuss the steps. Okay, to do that, I will do it by example, so it will be more easier to understood. So I will choose the transfer function here. Okay, so say we have g of s equal to s plus 1 over s times s plus 2 s plus 3, and for simplicity h of s is just 1. So we have unity negative feedback. Okay, steps. Step 1. Step 1 is a simple one, so we just need to determine the number of poles, the number of zeros, and the number of branches. Okay, so we know that g of s, h of s is the same as g of s because h of s is 1, so this is s plus 1, s plus 2, s plus 3. Determines. Okay, so I should write the rule first. So determine number of poles, number of zeros, and the number of branches. Okay, so for this open loop transfer function, then we have np is 3, right? Because we have 3 poles here, 0, minus 2, minus 3. Number of 0 is 1, which is minus 1. So the number of branches are 3. Okay, step 2. Determine where the root locus is crossing the real axis. Okay, so to do that, okay, let me draw the root locus. Like let me draw the axis. Okay, so this is the real, right? The real axis, real, say sigma, and then I have the imaginary, which is j omega, right? This is j 2j 3j, this is minus j minus 2j minus 3j, this is need more space, so this is minus 1 minus 2 minus 3, this is 1 2 3. Okay, now from step 1 we know that we have 1 0 at minus 1, so from the rule we should draw a circle at minus 1 because we have a 0 there. And for the triples located at 0, so this is the first pole, minus 2 second pole, and minus 3 the third pole. Okay, step 2, determine where the root locus crosses the real axis. So this is the real axis, and which part on this section the root locus will cross. Okay, to find the solution, then we just need to do uh, to compute the angles of this section. So the angles of g of s, h of s, so the angle of the open loop function must be plus minus 100 degree times 2k plus 1 for k 0 1 2 3 and so on. So the angle of the open loop transfer function must be an odd multiple of plus minus 180 degrees. Okay, so say for example, if the root locus is crossing this section here, so this section is on the real axis, right? Then any point here will satisfy this angle condition. Or say if it's crossing this portion of this real line, then it will also satisfy this angle condition. Okay, so let me copy this picture. So I will show you what I mean. Okay, now how many sections are there? We have 1 2 3 4 5. So from these 5 sections, which one of them is part of the root locus? We do not know, right? So we need to check them using this angle condition. Say at this section there's a point A, this section there's a point B, this section C, this section D, and for this section E. So we have 5 sections represented by these 5 points. So for point A, what is the angle? So the angle is the angle of point A from the poles, all of the poles on the real axis minus all of the so the angle of point A corresponding to all of the zeros minus the angles from all the poles. So the angles of that point with respect to all the zeros minus all of angles of all the poles. Okay, so let's compute the angle for point A. So point A is with respect to this pole at minus 3. Point A is at minus 180 degrees, right? So sorry, A is at 180 degrees, but since this is a pole, then the sign is minus, so it should be minus. The same with this pole. A is still at 180 degrees from this pole. Since this is a pole, then also the sign is minus. Next one, this is a 0, still 180 degrees, but since it is a 0, then the sign is positive 180 degree. Here is another pole, so minus 180 degree. So we have this cancels, we have minus 180 minus 180 times 2, right? So this is an even multiple of minus 180 degree, so it doesn't satisfy the angle condition. So in conclusion, the locus will not cross this section. There's no locus there, so let's put cross there. How about B? Well, B have the same angles with respect to these 2 poles and this 0, but for this pole it's just 0, so we have 0 minus 80 degrees plus 180 minus 180 is minus 180, which is an odd multiple of minus 180, right? Because when we set k is 0, we have minus 180 degrees. So yes, the root locus will cross this section on B. So we can draw a green line there representing the root locus. C. For C, we have 0, so 0 minus 0 plus 180 minus 180 is 0, so no. D, again, this will be minus 0 minus 0 plus 0 minus 180 degrees, which is minus 180 degrees. So yes, the root locus will cross that portion, this segment here. One last point, E, all of them are 0, so minus 0 minus 0 plus 0 minus 0 is 0, so no, the root locus will not cross this section. Okay, so far that's what we get. Step 3, let's move on to step 3. In step 3, we need to compute the asymptotes, and there are two equations. So first is determine angle of asymptotes, which is phi q is 1 plus 2q times 180 degrees over number of poles minus number of zeros for q 0, 1, 2 up to n p minus n z minus 1. Okay, for this, so let's compute for this case. So for this system, let's start. Okay, so what is np minus nz? So np minus nz, oh sorry, this should be 1, right, because it's a number. So np minus nz is 3 minus 1 is 2, so we have 1/2, and since it's 2 minus 1, so we have 1, so q is only for 0 and only for 1. So when q is 0, we have 180 degrees, which is 90 degrees. And also when q is 1, we have 1 plus 2 times 1 is 3 times 180 degrees is 540 divided by 2 is 270. So this is q1. How about the other angle is 1/2 times 520, right? Sorry, this is 540. 540, 1/2 is 270 degrees or minus 90. Okay, so you have two angles of asymptotes. One is at 90 degrees, then the other is at minus 90 degrees. Other than the angle, we need to also compute the point where the asymptote will cross on the real axis. So real axis crossing the asymptotes So here's the formula. So the point where the asymptote will cross the real axis, indicated by this sigma a, is the sum of the real part of the poles, so real part of the poles, and the sum of the real part of the zeros over np minus nc. So if you can see that we have two equations actually multiplied by 1 over np minus nc, so we have np minus nz on the denominator. So if np equals nz, then this equation will be infinity, right? Because np minus nz is 0 when np equals nz. So when the number of poles equals to number of zeros, we do not have angle of asymptotes. Okay, so you can keep that in mind. So let us compute the crossing of the asymptotes on the real axis for this case. So what is sigma a for this case? Sigma a so the real part of the poles, we have 0, minus 2, minus 3. So the sum of it, so 0, minus 2, minus 3, minus, we only have one 0, which is at minus 1, so minus 1 over 2, right? Because 3 minus 1 is 2. This is minus 5 plus 1 over 2, which is minus 4 over 2, which is minus 2. Okay, so I will copy this. So I will okay, I will copy this, copy, paste it here. Okay, so let's draw the asymptotes. Here we know that sigma a is minus 2, right? So the asymptote will cross at this point minus 2 on the real axis. So this point here, minus 2. What about the angle? Angle is 90 degrees and minus 90 degrees. So 90 degrees from minus 2 is this, and minus 90 degrees from minus 2 is this. Okay, so I should have used the thin, so let me just, okay, so these yellow lines are the asymptotes. Okay, that's step 3. Now step 4. In step 4, we need to compute the breakaway and or break-in points. So break away and or break-in points. To compute this, then we need to solve this equation. So dks over ds equal to 0. So what is k? So remember that we have this equation, right? So we can compute that k times g of s times h of s is equal to minus 1. So we put 1 on the other side, and we divide it with g of s times h of s, so we get k is minus 1 over g of s times h of s. Okay, so this should be a polynomial, so k of s. So this is k of s, and to compute the breakaway and or the break-in points, we need to compute the derivative of k of s with respect to s and then set it to 0. Okay, and then we need to find s star. So say s star are the roots of this polynomial or any solutions that makes this equation hold. All right, there okay, there are some of it. Note that dk of s for ds, since we have k of s given by this equation, so minus 1 over g of s times s of s, so dk of s over ds is g over ds of minus 1 g of s h of s equal to 0, right? And we can use the quotient rule of a derivative, and it turns out that this implies d over ds g of s times h of s equal to 0. Okay, so once we get s star, can be some of them, it's not only might be not only one, but also maybe 2, 3, and so on. We need to check if k of s star, so I will use index I, is real and positive for all I. Okay, then s star I is a break-in point if, so there might be some k of s star I for its I, right? And for break-in, then since there will be some of it, then put the minimum one, so the smallest k of s star I, so the minimum, so the s star that makes k to be the minimum one, the smallest one, and so the second derivative of k, so d square k over ds square equal to, and you substitute that equation with the s star I. If it's positive, then s star I is a break-in point. Similarly for breakaway, so it is a breakaway point, so this is away if k max, so the greatest one, and the second derivative substituted by s star of I is negative. So so either we will have either of it is a break-in or breakaway, only one of them. Okay, so let's do this for our example. So let's compute this. D over ds g of s is s plus 1 s plus 2 s plus 3, right, equal to 0. So we can use quotient rule, and I got s plus 3, sorry, s plus 2, s plus 3, all of them are squared. Here is minus 2 s cubed minus s squared minus 10s, okay, minus 6 equals 0, right? So this is this equation. We need to find s that makes this equation holds. Actually, you can see that any s should not be the roots of the polynomial on the denominator here, right? Otherwise this is infinity. So we just need to find the roots of this polynomial on the numerator. Since this is a third degree polynomial, then we have three roots. I have s star 1 is minus 2.46, s star 2 is minus 0.76 plus 0.79j, s star 3 is minus 0.76 minus 0.79j. So we have one real root and two complex roots. And let us substitute that to k. K star 1, I get 0.418, which is real and positive. Okay, that's a candidate of a break-in or breakaway point, which is still we do not know which one is it. And if I substitute the second one or even the third one, I have complex results. So 1.79 plus minus j for sorry, okay, plus minus 4.27j. Okay, since we need to check the one that is real and positive, so this is a good candidate of break in or away. So this s star 1 is a candidate of break in or breakaway point. So to determine whether it's a break in or breakaway, then we need to compute the second derivative. So k, and now substitute the second derivative of k of s and substitute it with k star 1, I get a negative value. So doesn't matter, it's negative. It means that this s1 star is a breakaway point. And that makes sense because what? Because from the rule we know that each branch starts from the poles and ends at zeros. We have a pair of zero and pole here. So this branch, this one branch starts from the pole and terminates at 0, so it will have this sign. So this arrow sign indicates that the root locus will start from this pole, ends at this 0. And how about this, the other two poles? We are asymptote, right? So, and we don't have any other zeros, so these branches, so this is the first branch. Since there are three branches, so there must be two branches here, one originating from this pole and the other one is originating from this pole. and will and where they will end up, they will go to infinity because we don't have any other zero, so they will go to infinity and they will approach this asymptote line. And since the root locus will start, so the branch will start from these poles, then of course we will have a breakaway, right? So somewhere there, which is minus 2.46. So let me copy this figure, copy and paste it here. Okay, so we know that on that point, which is minus 2.46, so this is minus 2, this is minus 2.5, so maybe somewhere around here. So this is minus 2.46. This is a breakaway. Okay, and I think we can start drawing the remaining branches. So it will start from this pole and that pole. They will meet at this breakaway point, and they will, as it say, it says breakaway, so they will break at this point and they will approach this asymptote like that. One will originate from this pole, the other is from this pole, so I have this arrow. So it means that when k is 0, then the poles are at this, the poles of the closed loop system will locate on these poles, but as k will increase to infinity, then the pole will move from that point to this. Similarly with the poles originating from these two poles, they will go to positive complex infinity and negative complex infinity. So for this case, I think we are done, but actually there are other two remaining steps which we do not need to apply for this particular case, but for other cases we might need to use them, so I will just explain it to you. The remaining steps, step 5. Okay, step 5, so determine angle of departure or arrival. So what is that? So when we have a complex poles or complex zeros, then we will need to compute the angle of departure or arrival. So for complex zeros, we will have angle of departure because so for this should be for angle for complex poles, because the root locus will originate from poles and it will arrive at 0, so this is angle for complex zeros, right? And angle of departure or AOD, it's symbolized by phi p, so angle of poles. Angle of departure is computed as 180 degrees minus the angle of that particular pole with respect to the other poles, so minus the sum of that angle with respect to the other poles plus the sum of angles with respect to all of zeros. So this is I angle CI, and this is a 0, 180 plus, so they have opposite sign. That's it. This is angle of arrival. Okay, that step 5, the last step, is determine the crossing of root locus at imaginary axis. Okay, so we see that from this plot the root locus will not cross the imaginary axis, so essentially we also do not need to perform step 6 for this particular case. So how to determine the crossing of the root locus on imaginary axis? So we need to solve this equation, 1 plus k times g of s times h of s, right, and set them equal 0, but we just need to substitute s with j omega because we are interested in finding the crossing of root locus at imaginary axis. So we just need to focus with the imaginary part of this complex variable s, right? So that makes sense. So by solving this polynomial, we shall obtain omega, and omega should be real. Okay, so let us apply. Since we know that the root locus will not cross, so it doesn't cross this imaginary axis, then there shouldn't be any solution to this. So let's see. Okay, so for that example I have 1 plus k, h of s is 1, so g of s is s plus 1, 1 0, so j omega plus 1, and then the poles are j omega plus 2, j omega plus 3 equals 0, right? So we can work on this, and I get minus k, so I will simplify it. I have 0 k minus 5 omega squared plus j minus omega cube plus omega 6 plus k. So this is complex, right? Since 0, then this should be 0, the real part should be 0, and the same with the imaginary part, it should also be 0. So what do we know? We know that k minus 5 omega square is 0. That's the first equation. The other is minus omega cube plus omega 6 plus k also should be 0. Okay, from here let us assume that if omega is not 0, so omega is a real number, it's not complex, and assuming that it's not 0, then we can divide this or multiply it with 1 over omega. Then we have minus omega square plus 6 plus k, right? But we know that k is 5 omega squared, so minus omega squared plus 6, and k is plus 5 omega squared. You have this polynomial 5 omega squared, sorry, should be 4, right? Because 5 minus 1, so 4 plus 6. And this is a quadratic equation, so omega is actually it's imaginary. It's not complex, it's not real, but it's only imaginary. So 1 plus minus j 1.2247. Since we need omega to be real and it turns out that omega is imaginary, then no crossing at imaginary axis. Okay, so when the root locus is crossing the imaginary axis, then we will have a real number solution for omega, and we can also determine what value of k that makes the pole crossing the j omega axis. Okay, so that's the end of this lecture. For the session for next week, I will be solving more problems on drawing root locus. Alright, thank you. I'll see you next time.